Okay, let's go through experiment 17. And I know I'll be going through the applications of principles with you, but what I'd like to do first, is just go through the experimental procedure. Unfortunately, we won't be able to do that, but I think it's important for you to go through the experimental procedure so we can actually predict what we should see happen. That's, to me, the nice part about Le Chatelier's in chemistry is that if you understand the principles and you can predict what's going to happen, it makes it a lot more fun because it verifies your understanding. So, first of all, we're going to be looking at a weak acid. This is acetic acid. Okay, and remember your 7 strong acids are hydrochloric acid, hydrobromic acid, hydroiodic acid, nitric acid, sulfuric acid, perchloric acid, and chloric acid. And when we're looking at acids and we're talking about aqueous solutions, and it's not one of those 7, then you're going to consider it weak. Okay, so this is acetic acid, not one of the 7. It's a weak acid, so it goes into an equilibrium. Most of it stays in the molecular form, but some of it ionizes to give you H plus and acetate. So my equilibrium constant expression, this is my equilibrium constant expression, products over reactants, is going to be the concentration of H plus times the concentration of acetate over the concentration of the molecular form of acetic acid. In our experiment, what we would do is we would have a test tube and you would put in a few milliliters of the 0.1 molar acetic acid and you add in an indicator called methyl orange. And methyl orange is red, pinkish red, if your pH is less than 3.1. But when it becomes more basic, so your pH goes above 4.4, it'll go from red to orange to yellow. Okay, now here, remember my indicators, if I'm looking for the acid, I'm not looking for this, I'm actually looking for H plus. Alright, so when I first put this together, I will have some H plus in there. And so my pH is going to look kind of reddish orange. The question is, what happens when you add sodium acetate? Remember, sodium acetate is an ionic compound. And so, because it's an ionic compound, it will dissociate into sodium ion and my acetate ion. Okay, so really what I'm saying is when I add sodium acetate, what I'm doing is I'm increasing my acetate concentration. So when this goes up, the question is, what happens to H plus and what happens to the molecular form of acetic acid? Well, here's K, and remember we're talking about Q, when it's non-equilibrium, is going to be the same expression. If I increase my acetate concentration, then this goes up. That means Q will be larger than K. So my reaction goes left. Okay? If it goes left, then some of my acetate will use H plus to form my molecular ion. My molecular form of acetic acid. So when this goes up, this one goes down, and that goes up in order to try to get back to my equilibrium state. Okay? So if my H plus concentration goes down, that means my solution is less acidic. So my pH will begin to increase. And so here, what we will see is it will go from red, orange. As I add my acetate, I use up my H plus, so my pH increases in value. so it becomes yellow. Okay, so this is how we explain our first observation. Our second observation in this experiment is you have your test tube, and again you have basically your methyl orange and your acetic acid. Okay, so for the second test tube, what we're going to add, okay, hold on, let me just make sure. Oh, sorry, not acetic acid, it's ammonium hydroxide. I'll shift this over. Okay, so this one has ammonium hydroxide and phenolphthalein. And phenolphthalein when it's acidic, okay, so my pH is less than 8, 7 actually, is colorless. As my pH is greater than 8, it starts becoming pink until it becomes a bright pink. Okay, so ammonium hydroxide is a weak base. And so my equilibrium equation looks like this. So if I have ammonium hydroxide and phenolphthalein, and I know it's a weak base, then this will be pink. Now, what I'm going to do, write down my K expression, which is the concentration of ammonium ion times the concentration of hydroxide ion over ammonium hydroxide in its molecular form. Okay, so for my first test tube, you're going to add ammonium chloride. Okay, when I add ammonium chloride, basically what is this? This is ionic, so I'm adding ammonium ion and chloride ion. And this is what we're after. Okay? This is a common ion effect. This is increasing the concentration of ammonium. So if I increase the concentration of ammonium, then Q, I'm increasing my product, is larger than K, so my reaction will go left. If it goes left, then to compensate for this increase, because you're adding in ammonium ion, then it's going to consume some hydroxide in order for you to produce the molecular form of ammonium hydroxide. So it's going to decrease hydroxide, increase ammonium hydroxide, so I can get back to my equilibrium state. Okay, so if I'm decreasing, my base is going to become less basic, more acidic. So then my test tube will lighten up and then become colorless. So it goes from pink to colorless. Okay. Now what happens if we try this again, but in this case, I'm not adding ammonium chloride. I'm going to add hydrochloric acid. So, with the ammonium hydroxide in another test tube, my equilibrium still stands. But in another test tube, I add hydrochloric acid. Okay. Well, it turns out when I add hydrochloric acid, how does that relate to ammonium hydroxide? Well, there's nothing common because I'm adding H plus and Cl minus, but I have a competing reaction. And the competing reaction is H plus OH minus gives me water. Okay? So when this happens, that means I'm decreasing the amount of hydroxide I have. If I decrease the amount of hydroxide I have, I'm losing product. Q is going to be less than K because I'm losing product. So that means that my reaction goes right. Okay, so as a result of my hydroxide concentration decreasing, I dissolve more ammonium hydroxide, so this goes down and this will increase. And this is to compensate for this decrease to get back to my equilibrium. So if it goes right, because I'm losing hydroxide, then again, I'm no longer as pink. It'll start becoming colorless. So the pink goes to colorless. Okay? And if you see something like, but I'm adding acid, of course it's going to be less basic. That's true. But it's important to also consider how it affects our equilibrium. Okay? So let's talk a little bit about the next reaction. Okay? So our next reaction looks like this. And the reason I want to spend time actually about going through all these reactions is then we will apply the same kind of approach and logic when we do the application of principles. So let's go ahead and do the next one. So the next one looks like this. My equilibrium equation, you take iron 3, you're going to add thiocyanate to it. These are all aqueous. And you're going to get a thiocyanate complex. And it turns out this is a very dark red. It's like a wine red or a blood red, actually. Sometimes. Okay? So when you first make it, you're going to make, since this is such a dark red, you're going to make several test tubes. And in there, you're going to have your complex. So this is all your test tubes will be a dark red. Okay? So let's go through and write down our K expression. So K is product over reactants. Okay? And the first thing we want to do is this. So once we make all of our solutions, then the first one you're going to add iron 3 nitrate. Okay? When I add my iron 3 nitrate, what am I really adding? This is an ionic compound. We know our solubility rules tells us that my nitrate always soluble. So what we're really adding is iron 3 and then the nitrates. Well, if I look at my equilibrium reaction, it's the iron 3 that's going to have the impact. And what I'm doing is I'm adding reactant. If I'm adding reactant, then Q is going to be less than K. So my reaction goes right. If it goes right, what I'm going to do is some of my iron 3 that I've added now reacts with my thiocyanate, so that concentration will go down. And I increase the amount of complex, so that at the end you're going to get K again. You're going to go back to your equilibrium. But if I'm increasing my complex, I'm increasing the amount of compound in my solution that has a red color. So what happens, what we should see, is it's red and then it gets darker. Okay, because I'm increasing the amount of my complex that contributes to the red color. All right, so let's now look at test tube number 2. And so far, everything that we've been doing has been affecting concentrations, either directly or indirectly. So let's take a look at test tube number 2. I should have erased my test tube here. Okay, so here's my test tube number 2. Okay, this has my iron thiocyanate complex in it, and it should appear red. Okay? And with test tube number 2, what we're going to do is we're going to add potassium thiocyanate. Again, this is an ionic compound. So what we're adding is potassium ion and thiocyanate ion. Well, this isn't part of my equilibrium reaction, so I'm going to ignore the potassium ion. But what we do see is this. I'm adding thiocyanate. So I'm adding, again, reactant. If I increase my reactant here, then we know that Q is less than K. So my reaction goes right. Okay? If my reaction goes right, that means that this needs to be consumed in the reaction so I can increase the amount of complex I form in order to try to get back to equilibrium. So the whole reason this is happening is I'm at equilibrium, I disturb it, and it wants to go back to equilibrium. So it's going to adjust itself by changing the other concentrations of my reactants and products in order to get back to equilibrium. If I'm forming more of my complex, then I'm forming more of the compound that makes the red color. So it's going to become a darker red. So that's test tube number 3. Or 2, excuse me. Let's take a look at test tube number 3 now. So test tube number 3. Test tube number 3, I'm actually adding sodium hydroxide. Okay, so I'm adding sodium ion. That doesn't seem to have an effect. I'm adding hydroxide. And if you initially look at it, that doesn't seem to have any effect. But now let's take a closer look. If I add this and I form sodium thiocyanate, that's pretty much nothing's going to happen. They'll stay in solution. Remember how we did all those molecular, total ionic, and net ionic equations, okay? However, if I look at the reaction between iron 3 and hydroxide, you get, oh, I guess I'll toss this one. What you get, you have iron 3 reacts with hydroxide, 3 of them, and what you get is you get a solid. Remember, hydroxides are mostly solid, okay? And this is actually a yellow solid, a yellow-orange, okay? So now you say, well, wait a second, maybe the sodium hydroxide will affect my equilibrium reaction. Because what it's doing is that once I form the solid, that comes out of solution. That just goes to the bottom. So what happens to my iron 3 ion that's available to make the complex? There's less of it because it's all in this solid material. So as my iron 3 concentration decreases, when this goes down, that means I have too much product. That means Q is greater than K. So my reaction goes left. Okay? And in this case, it's not because I directly added reactant or product. It's because I have a competition that's removing my reactant from solution. So when I remove this, this goes down. So now I have to decrease the amount of product to try to compensate for this going down. And so I end up increasing my thiocyanate. Goes left. When it goes down, you're going to see a couple things then. You're going to see a red, orange, yellow-orange. Sorry. The yellow-orange precipitate. So you're going to see solid form. Okay? And since I'm using up my complex, my red will disappear. So it'll lighten to light red, colorless. Okay? Because I'm losing the complex that's making my red color. Okay? Now what about the last one? The last one's a little tricky, so I'm going to throw out some numbers for you too. Not because they're the real numbers, but the numbers just for comparison's sake. Okay? And that is for your 4th test tube. All you're going to do is add water. So the question is, what happens? And lots of people think nothing happens. I'm just adding water. It's just my solvent. But then when we talk about it, then it says, oh, that makes a lot of sense. So let's just go through. When I add water, what am I doing? I am diluting, okay, my solution. Alright? So everything goes down. That concentration decreases, that concentration decreases, and this concentration decreases. So the question is, with all my concentrations decreasing, how is that going to impact my equilibrium? So I'm going to use a different color, and I'm just going to give you some reference values, but they're not necessarily the true values. The reference values is only so that you can quickly analyze and see what happens to K and Q. So suppose K is equal to, let's say, 1 molar divided by 1 molar divided by 1 molar. Okay, So let's say just say K is equal to 1. So this is my reference. Okay. Now let's dilute it. So if I dilute tenfold, all my concentrations now are equal to 0.1 molar. Okay? So let's take a look at what Q would be equal to. So Q, because I know I'm not at equilibrium, but I don't know where I am. So let's find out. 0.1 here divided by 0.1 times 0.1. Okay? That's equal to 10. So Q is greater than K, which means my reaction goes left. If that's the case, then because I diluted it, my reaction goes left. I'm going to have to take some of my complex to make my iron 3 and my thiocyanate. So my solution becomes a lighter. Is this always going to be the case when you dilute a solution with a complex like this? And the answer is no. Like if you were making punch, if you were making orange juice, yeah, it looks lighter in color. But you'll have to take a look at your equilibrium expression to know exactly what direction my equilibrium is going to lie. Okay, so we're talking about now the chromate dichromate ion equilibrium. Turns out when I have the chromate ion in solution, my solution's yellow, but my chromate reacts with acid to give me dichromate in water. And the dichromate ion is orange. Okay, so this is a really nice way of determining our equilibrium because we can see the yellow and the orange changes. So our K expression is product over reactants, and notice it's squared here and squared there because I have my coefficients of 2 here. And in the lab, what you're going to do is you have your test tube and you're going to have your chromate. So it should appear yellow. So what you do is you're going to add sulfuric acid. And the question is, what happens? So when you add sulfuric acid, remember, sulfuric acid dissociates as a strong acid. So it dissociates completely. So what you get immediately is a bunch of H+. Now if I'm adding an H+, I'm adding reactant. So this goes up. That means Q will be less than K. So as a result, my reaction goes to the right. And when it goes to the right, then what happens is this. It goes to the right, this gets consumed, and I increase the amount of dichromate that I have. So when it goes to the right, and the dichromate concentration increases, what color is that? It's orange. So my solution goes from yellow to orange. Okay? And then, what happens next? Well, what happens next is you're supposed to add sodium hydroxide. So when we take this, so now we have an orange solution. and it has my dichromate. And to this solution, I'm going to add sodium hydroxide. And so when you add sodium hydroxide, what happens? The hydroxide reacts with H plus to form water. So now what we've done is by adding sodium hydroxide, we're removing H plus from solution. So we're decreasing the H plus. Because of that, Q is going to be greater than K, so my reaction goes left. And when my reaction goes left, then because this decreased, then this has to decrease because I need to form more chromate. So this will decrease and my chromate will increase. When that happens, since my chromate is increasing and it's yellow, then my solution turns yellow. Okay, so now that my solution turned yellow, what's going to happen what's going to happen when I add sulfuric acid again? So I add sulfuric acid, turned orange. Then with the dichromate solution, I add sodium hydroxide, turns yellow because it went back this way. Now I add sulfuric acid again. And guess what? I added more reactant, so it's going to go to the right. So it's going to turn orange again. Okay? So we're just, what is this doing? We're just playing back and forth at base, at acid. You can go back and forth as much as you want, and you're going to just be playing with Le Chatelier's principle and affecting your equilibrium by having these color changes. Alright? Now let's take a look at saturated solutions. Okay? So now we're going to be looking at heterogeneous equilibrium. Okay, so what we're looking at is solid sodium chloride, and it becomes aqueous sodium ion plus my chloride ion. Remember, I'm at a saturated solution when I establish my equilibrium. Okay? So, one moment. Okay? So, now that we have our equilibrium equation for our saturated sodium chloride solution, let's write down our K expression. And our K expression looks like this. Concentration of sodium ion times the concentration of chloride ion. What about the sodium chloride? Because it's a solid, it's not included in our equilibrium expression. So, what you do is you have a saturated sodium chloride solution here. Okay, so it's about 5.4 molar. Okay, and what you're going to do is you're going to add hydrochloric acid in it. That means you're adding H plus and Cl minus. Well, the H plus doesn't have any bearing, but my chloride ion does. So if I add more chloride ion, then this goes up. But if this goes up, then my Q is greater than K, so my reaction goes left. If it goes left, then my chloride is going to react with the sodium ion to produce sodium chloride. So that goes up, this goes down in order to preserve K. They're inversely proportional. What that also means is that I form a solid because I'm going left. So you're going to see precipitation. When you add HCl to this solution. Okay, let's take a look at another one. Okay, so the next heterogeneous equilibrium equation that you're going to look at is this one. Barium chromate is a solid, and it gives you barium ion and chromate ion. But here's the thing, in this scenario that we're going to be approaching, okay, what we're going to do is, when we look at this, we're going to have to also look at a competing reaction. So let's write down the K for this one. And that's just my barium ion times the concentration of my chromate ion. Okay. So, for step one, when you have your solution and you add barium chloride, okay, plus potassium chromate, you're going to see precipitate form. This part is just a double displacement reaction. And this will be my product. But what else is this? What is a double displacement reaction? The fact is, you're still going to have some potassium chromate in there. So the solution becomes yellow because of the chromate in solution. Okay, so you would expect to see a yellow solution and solid form on the very bottom. Okay, so when you do step one, when you mix barium chloride solution plus potassium chromate solution, you'll see solid barium chromate and the yellow solution. And this is because of the chromate. Okay? And then you're supposed to add some hydrochloric acid. Okay? So let's take a look to see what's happening. If I add hydrochloric acid, what happens? Well, you're adding H plus and Cl minus. So when you look at this equilibrium, barium chloride, we added barium chloride, so that's not going to do anything. So really it has to do, does acid and chromate ion do anything? And that's where we get to our second equilibrium. Okay, remember our second equilibrium that we talked about previously was this. If I take my chromate ion and my acid, I form dichromate and water. This is orange and this is yellow. Okay, so K is equal to the concentration of my chromate divided by my dichromate divided by the chromate concentration squared and the H plus concentration squared. Okay, so let's walk through this. When I add H plus and Cl minus, it doesn't affect, this is what we're interested in, right? It doesn't affect this directly. What happens is that H plus reacts with the chromate, so it forms dichromate. So in my test tube, all the chromate that's there, the yellow, will turn to orange, because now I'm forming dichromate. But it goes even beyond that. If I start using up my dichromate, if I start forming dichromate, I'm using up all my chromate. That means in this equilibrium equation, my chromate concentration decreases. Okay? If my concentration of the chromate ion decreases, that means my reaction goes to the right. Okay? So when this reaction goes to the right, well, this is decreasing because I'm using it up here. That means my barium ion has an increase, but that means that I'm going to be dissolving my solid. Okay, because it's all being dissolved to go to the right to increase my barium concentration and to make up for the loss of chromate because it's being consumed here. So when you add in your HCl, your solution's going to turn orange, and all of that precipitate on the bottom, all your solid precipitate dissolves. Okay, so those are the predictions that you're going to have based on your understanding and knowledge of Le Chatelier's principle. Okay, now let's go through and work our application of principles. With the application of principles, I will be taking it a little bit slowly. I apologize, but there's a bit of a thought process that goes in here, right? So, we have a 2-liter container. Okay? And in my 2-liter container, I have this reaction. Dichlorooxide gives me chlorine, oxygen, and energy, which means it's exothermic. Okay, so right away we know our reaction is exothermic. And then we're going to, once we reach equilibrium, we're going to stress it and then determine, basically, is it going to go right or left? Okay, So let's just write down our K equation. It's products over reactants. Okay, so the first one, we increase concentration of chlorine oxide. Okay, so if we increase that, then Q is going to be less than K, because I have a bigger number here. It's like comparing 1/2, and if I increase it to 1/8. So if this is K and this is Q, we know Q is less than K. All right, just giving you some reference number. So then my reaction goes to the right. If I increase this, I go to the right. I increase, okay, my chlorine and my oxygen. So basically you want to know, does it shift? And the answer is it shifts right. Okay, so the next one is I increase my oxygen concentration. Again, Q is going to be less than, hold on a second. If I increase my oxygen, this goes up. Q is greater than K. I'm adding in my product. Therefore, it goes left. Okay? For C, I decrease my chlorine concentration. If this number goes down, then Q will become smaller. So if Q is less than K and I decrease this, then I want to go to the right to increase the amount of chlorine. So it goes right. Okay, now D, I say I increase pressure. Can't spell pressure. By decreasing the volume. Well, if I increase my pressure, I have 3 moles of gas on the right-hand side. I have 2 moles of gas on the left. So to relieve the pressure, then I'm going to take the smaller number of moles. So when we talk about pressure affecting it, if I increase the pressure, it's going to go to the left. If I decrease the pressure, it'll want to go to the right. Suppose I increase the temperature. Well, remember, my energy is on the product side. This is an exothermic reaction. If I increase the temperature, I'm basically increasing the amount of product. Well, that means that Q is basically going to be too large. So my reaction has to go to the left. Okay, F. Okay, we add a catalyst. Okay, so if we add a catalyst, nothing happens. Because remember, catalysts affect, catalysts affect our rate, how fast the reaction goes, but doesn't affect the equilibrium constant. And G, so to the 1 liter container. So we are going to add helium to the 1 liter container. Okay, so this is kind of like a dilution, right? So think about it this way. I want to spend time on this one. Okay, so we're just going to take these numbers, all right? So let's say in the 1 liter container, when I reestablish my equilibrium, let's just say I have 1 atmosphere of chlorine gas, 1 atmosphere of oxygen, and 1 atmosphere of dichlorine oxide. Okay, so let's just say K is equal to 1. All right? Or we can say 1 molar. But I will just stay with 1 molar. Okay, so Kc is equal to 1. Now, what happens when I add my helium? Okay, so the concentrations, do the concentration of chlorine gas change? No. If I say I have 1 molar in 1 liter, it's the same. So Kc will remain unchanged. Okay? Make sense? So I have a 1 liter container. Let's say I have 1 mole here, 1 mole of this, 1 mole of that. That Kc is going to be 1 at equilibrium. If I add helium, then what is the concentration then? Okay, of my chlorine? It's going to be the same. Because the volume is not based on the helium being present. The volume is only based on the volume of your container. Okay? All right. Let's move on. For number 2, okay, we're going to do the same thing. We're going to look at the direction at which something is going to shift. So I have silver acetate as a solid, and it's in equilibrium with the silver ion and my acetate ion. Okay, so here's my Erlenmeyer flask. Okay, I have 1 liter of the solution. Okay, the other thing I'm going to do is I'm going to write down my K equilibrium, which is just equal to the concentration of my silver ion and my acetate ion. Okay, and just make sure I'm in equilibrium. I'm going to add just a little bit of my solid in here so I know I have a saturated solution. Okay, so let's go through and take a look. If I add silver nitrate, okay, to my solution, and it says solid, but here's the thing. When I add silver nitrate to my solution, the reason it says solid is this. I don't want to change essentially the volume, okay, of this. Otherwise, we'll have to worry about changes in our concentration as well. So if I just add it in the solid, when it dissolves in my solution, it'll give me silver ion and nitrate. Nitrate's not going to affect it. But silver ion means I'm adding product, which means my Q will be larger than K. So my reaction will have to shift left in order to compensate for the extra product. This will decrease. I added this, and then I see more precipitate, so it shifts left. If I add sodium acetate solid, again, this is an ionic compound that's highly soluble. We're not that interested in the sodium ion because it's not going to affect our equilibrium equation, but adding acetate will. I'm adding product again. So Q is greater than K, and so it's going to shift left. Right? What happens when I add 6 molar nitric acid? Okay, so we have the H plus, okay, in nitrate. Nitrate's not going to affect it, but here's the thing, we have a competing reaction, and that is, remember, H plus C2H3O2 gives me a weak acid, and that's acetic acid. So I establish an equilibrium right here, which means I'm consuming my acetate. So when I add my nitric acid, my product goes down here. So to take care of my equilibrium, my Q, since I've decreased this, is less than K, is going to shift right. And we're going to see more silver acetate dissolve. Okay. What happens if I do this? What happens if I add solid silver acetate? Okay. Well, it's not part of my equilibrium reaction. And remember, the concentration of this isn't involved because it's basically a constant. So I'm not adding anything that's going to affect my equilibrium. You say, well, wait a second, aren't I going to add more reactant? Yes, but that doesn't mean more of it's going to dissolve. It's not. It's just there. So this is unchanged. Okay? And last, what happens if I add 100 milliliters of water? Okay? And like what we did when we were looking at the experiment, so let's just say that K, if the silver ion needs to be 1 molar and the acetate ion needs to be 1 molar. Okay? So let's say K is equal to 1. If I add 100 milliliters of water, I'm diluting my solution, which means my concentrations will go down. So Q would be equal to, let's say, 0.1, 0.1. So this means that Q would end up being less than K. So when I add in my 100 milliliters of water and I'm diluting it, and this goes down and that goes down, Q will be less than K. These numbers are just so you can compare to see why Q is less than K, which means it goes to the right. And so it's no longer, when I add 100 milliliters of water, it's no longer a saturated solution. So I'm going to end up dissolving more solid to form my ions to get a saturated solution again, to reach equilibrium. Okay. So let's move on to number 3. Okay. So for number 3, the question is, will these dissolve in water if I add nitric acid? Okay, so let's take magnesium carbonate. Okay, so before we can answer it, let's write out our reaction, our equilibrium reaction, and the K expression in order to analyze this. So this is a solid in neutral water, just water. And when a little bit dissolves, there's an equilibrium here that looks like this. Okay. Now if I add H plus and nitrate to the solution, let me write you the K expression too. So K is equal to magnesium ion times carbonate. Okay. when I add nitric acid, a direct effect doesn't occur. There's no common ion, there's no magnesium here, there's no carbonate here. And if I do a double displacement, magnesium nitrate stays in solution. But here's the thing, H plus carbonate gives me carbonic acid. This is a weak acid. And this could also dissociate to H2O and CO2 gas. So by adding acid to this, what happens is I have a competing reaction, and this is going to use my carbonate ion. Because my carbonate ion is being used in this reaction, this concentration will go down. Therefore, Q is going to be less than K. So my reaction will go right. Okay? So the question is, will this dissolve? And the answer is yes. It'll dissolve. And write the equation for the reaction or reason for no action. So here is the equation for, this is the reaction. You have a competing reaction that uses that consumes the carbonate, which is my product. Okay, so that's the first one. Okay, let's take a look at the next one, silver chloride. So if we look at the next one, silver chloride, B. Okay, so if I take silver chloride, the first thing we're going to do is write down our equilibrium reaction. And then let's write down our K. Alright. Now when we do this, I'm introducing H plus and NO3 minus. So HCl, that too is a strong acid, so there's nothing that's going to happen there. Stay in solution. Silver nitrate, always soluble, nothing is going to happen. So nitric acid does not affect the silver ion concentration nor the chloride ion concentration. So, no, the addition of nitric acid does not make it dissolve. Okay? So this is the reason for no action. Alright, so let's take a look at the third one, calcium phosphate. So again, first order of business is always write down your equilibrium reaction. And then the next order of business we're going to do is write down our K expression. K is equal to my calcium ion concentration cubed times my phosphate ion concentration squared. And this being a solid isn't involved. Now, let's take a look at the addition of nitric acid. So, when we look at a double displacement and look at calcium nitrate, that's always soluble. So these two are going to stay in solution and not be affected. What happens if I react in H plus with phosphate? Now, if I look at H plus with phosphate, I get phosphoric acid. This is a weak acid. What does it mean? Remember, a strong acid dissociates completely. So like nitric acid, strong acid, where all of the nitric acid, none is in the molecular form. You're going to just get H plus and nitrate. But what's interesting is whenever you have a weak acid, most of it will stay in the molecular form, and very little of it will ionize out into its component ions. Enough that you can see it, detect it, we can measure the acidity, we can see it because it's a weak electrolyte, but it's not 100% dissociation like with a strong acid. In that case then, what's going to happen is all my phosphate will be bound up in the molecular form of phosphoric acid. So this concentration will decrease. If this decreases, that means Q is going to be less than K. So it will go to the right. So yes, calcium phosphate will dissolve upon the addition of nitric acid. And the reason is you have a competing reaction right here that consumes my phosphate. Okay, which is one of my products. Okay, so that is C. Let's take a look at D. So for D, the question is, I have zinc sulfide, and I want to know if this will dissolve upon the addition of nitric acid. And what do you think the answer is going to be? Okay, I think you ought to try to just hit pause and see what you think. Okay, let's talk about addition of nitric acid. Zinc nitrate is always soluble. So my zinc ion will stay in solution, my nitric ion will stay in solution. The question is, what happens when I react my H plus with my sulfide? So, when I react my proton with sulfide, you form hydrogen sulfide gas, okay, which can bubble out of solution. So, because of that, and whatever component stays in solution, it's a weak acid. So, again, like we've seen in the previous problems, this is my competing reaction. Okay, so if my sulfide concentration goes down, then Q will be less than K, which means my reaction, the zinc one, goes right. So, yes, it will dissolve upon the addition of nitric acid. Okay, let's do one more, and then we have one more problem left in our application of principles. The last one is the barium sulfate. If I have barium sulfate, okay, and I form my barium ion and my sulfate ion. K is equal to barium ion concentration times my sulfate ion concentration. So the question now is what happens when I add nitric acid. So when I add nitric acid, barium nitrate is always soluble. So nothing happens to my barium concentration. It stays the same. It's not going to be touched. What about reacting H plus and sulfate? Remember, sulfuric acid is a strong acid. And a strong acid means it dissociates completely. Okay, which means adding H plus to my sulfate is going to do nothing. It's going to stay in solution. So in this case, my barium ion and my sulfate ion concentrations remain unaffected. So, no, does not dissolve. Okay, so we know then adding nitric acid to barium sulfate will have no effect. Okay, let's take a short break here. Okay, so let's go on the last question on our application of principles. What we have is we have basically nitric acid, nitrous acid, and it's in equilibrium with H plus and the nitrate ion. Okay, so we have a liter of this equilibrium solution. And what we're doing then is we're going to write down the K expression, so H plus concentration times the nitrite concentration divided by the nitrous acid concentration. And the first question says, what happens to all of my concentrations to the equilibrium concentration? So once I've established equilibrium, now I'm disturbing it by adding 1 mole of nitrous acid. When I do that, then my nitrous acid concentration will go up. When that happens, my Q, right, is going to be less than K because I'm adding more reactant, which means that my reaction, my equilibrium reaction, will go to the right. When that happens, I'll get greater dissociation. So from equilibrium concentrations, my H plus will see an increase and my nitrite will see an increase. Okay. What would happen if we do this? We added 6 molar HCl. Okay, so remember this is a strong acid. I'm adding H plus and I'm adding Cl minus. Well, my chloride isn't going to have any effect. Okay, but I'm adding H plus, and you can see that means I'm adding product. So my Q is going to be greater than K, so my reaction will go left. Okay, so if we look at the concentrations, I have added 6 molar HCl, so I've increased my H plus concentration. Now, because I'm going left, that means from my equilibrium concentration, I increase my nitrous acid because I'm going this way. But, oops, that's not chloride, nitrate. But in order for me to form more nitrous acid, I have to use up, I have to consume some nitrite, which means this decreases. Okay? So I for increase, D for decrease. Okay? Let's take a look at another scenario. What happens if I add 1 mole of solid sodium nitrite? So what we're saying is we're adding sodium ion and we're adding nitrite ion. Okay? So if this is the case, then basically I'm adding more product. So my concentration of my nitrite will go up, which means Q is greater than K, so it goes left. Okay? So my nitrous acid concentration, since I'm going left, I'm forming more of that, so it will increase. To form this, I need to consume some H+. So my H+ concentration will decrease, and my nitrite concentration, because I added more in, that increased from my equilibrium value. Okay, so if I increase my nitrite, it goes left, it's got to consume some of this in order to form more nitrous acid. Okay? Alright, what happens if I add water and I dilute it? So basically, I have diluted it. Okay? So, from my equilibrium concentration, this went down, that went down. Okay? They all went down. Because I diluted it, that value won't be the same anymore. Now, because I diluted it, this goes down, and these guys go down, my equilibrium will shift, okay? And so, in this case, it will shift left. So let's just do an example. Let's just assume K is 1 molar for everything. And if I dilute it 0.1, 0.1, tenfold, and that means Q is less than K. So it's going to dilute, it's going to basically go to the right. So when I dilute it, even though it goes right, the question says, how does my concentration change relative to the equilibrium concentration when I first started? And the bottom line is this: everything decreased. I can change it by going to the right to try to get back to equilibrium, but I will not be able to get back to my original concentrations before I added my water. So my equilibrium shifts to the right, but if I look compared to my original equilibrium concentrations, I'm not going to get back to those values. Okay? Finally, let's take a look at adding sodium hydroxide. Okay? So when I add sodium hydroxide, I have a competing reaction. And that is H plus OH minus gives me water. So, because of this, my H plus concentration will decrease. So Q is less than K, my reaction goes to the right. Alright, so if I go to the right, then it looks like this. I need to use some of my molecular nitrous acid. So that's got to decrease in order to compensate for the fact that my H plus concentration decreased. And when I try to make more of this, I also make more of my nitrite. So my nitrite ion will have increased with respect to its equilibrium concentration. Alright, so this is how we evaluate the Chatelier's principles and how it helps us to determine and predict which way our equilibrium reaction will go once we actually disturb it from equilibrium. Alright, and that's the end of experiment 17.